So in this lecture number 30, we are going to talk about differential analysis. Previously, we developed the integral form of equation for a control volume. So we developed integral form of equation for control volume, for mass conservation and for momentum. Now they tell us about the overall gross behavior of a fluid flow and its effect on various devices. However, it does not provide point by point knowledge of the flow field. For example, let us say that we have an aerofoil and there is flow happening over it, and in this way we are having flow over it. So in this case of an aerofoil, if we are going to do control volume analysis, then it would tell us about, let's say if we are interested in, then how much lift would be generated and how much would be the drag force, things like that. It would give us bulk values, overall values, but it would not tell us that what kind of pressure distribution actually resulted in this lift. So it would not give us point by point value, and many a times it is possible that we are interested in more detailed study, and that is the place where we want to know more details of the flow field, and there we need to apply differential approach. Now previously in unit 2 we already covered mass conservation equation using differential approach, and this equation 1 by rho d rho by dt plus del dot v equal to 0, where rho is your density, d by dt is the material derivative, or you can say Lagrangian form derivative, plus del dot v, divergence of velocity, where v is the velocity, is 0. This is something which we already derived in previous unit. Now we are going to do the differential analysis for our equation, momentum equation, and we would see. By the way, for the mass conservation equation, here we have not taken any assumption of steady, unsteady, or compressible, incompressible, or anything like that. I would rather say, assumptions which we have considered here are that the density and the velocity are continuum functions. Other than that, there are no assumption. But to start with, when we are going to talk about we are going to talk about momentum equation differential analysis, we are going to take this assumption of inviscid flow, okay, and we assume that the effect of viscosity can be neglected once we are talking about inviscid flows. Now, viscous action usually originates at the solid fluid boundary. So for example, let's say we have a solid here, and on top of that there is fluid. Then viscous effects actually start generally, most of the time, at the solid fluid boundary, and this happens due to no slip condition, meaning by that at the layer where solid is adjacent to the fluid, they both would have same velocity. There is no slipping happening. So the velocity, let's say, of solid and fluid which is adjacent to this solid would be same. And because of this, we see viscous effects happening. So near the boundary there are more viscous effects. As we move away from the solid fluid boundary, viscous effects become quite small, so small that we can neglect them. So let's say if we are talking about a flow, and here we take a fluid particle, and what is a fluid particle? We are saying that fluid particle, we are not saying it is molecule or it is atom, but we are saying fluid particle is the smallest dimension which you can consider under the continuum concept. So let's say we want to analyze fluid flow. So what we would have to do, we need to, and let's say this particular particle is moving this path. Along this path, what is happening? So we are following a fluid particle now. We need to see what is happening to it. For that, we would be applying the basic laws available to us. Okay, so let's say what we would have to do is to apply the basic laws which we know. So what are those basic laws? We know about mass conservation, and we know about Newton's second law, which is momentum equation. These are the two laws which we have. So let's say if I want to apply Newton's second law to this particular fluid particle, which is moving in such a flow that that flow is considered inviscid. So to do that, sum of all forces on fluid particle. This summation of all forces would be equal to mass times acceleration. This is Newton's second law. And we know that there are two kinds of forces which are being applied: surface force and body force. So summation of all surface forces, summation of all body forces, this would be equal to mass times acceleration, and that would be density multiplied by volume of this particle. So rho is the density of the particle, del V is the volume of the particle multiplied by acceleration. And again, we have taken this acceleration in inertial frame of reference. What do I mean by inertial frame of reference? That there is no acceleration. Okay, I'm not taking accelerating frame of reference, but inertial frame of reference, meaning by either my frame of reference is at rest or moving at a constant velocity with respect to the global frame of reference. Now, there are two types of surface forces which we are considering here. One is the viscous force, and the other is the pressure force. Okay, FB is the body force. Now, because of inviscid flow, we have taken this assumption that the viscous effects are not present. Okay, so my viscous summation of Fs, surface force, would only be due to pressure force. Let me write that as Fp. Now let us see what it is going to be. This would be minus del P for the whole volume, and this is nothing but pressure force per unit volume. Okay. Now my body force would be volume, again, which volume? Volume of the fluid particle multiplied by body force intensity. This B here is nothing but body force intensity per unit mass, per unit volume. Actually, that would be body force intensity per unit mass, B. If I put these things back in my equation above, then I would get minus, and this minus sign for the pressure force, since pressure is compressive in nature, that's why this minus sign, del V plus B rho del V plus equals to rho del V times A. Now in most of our cases, this B is actually due to gravity. We are considering body force due to gravity most of the time only, so B would be equal to G. But let's say if there are other body forces, then we would have to consider that. And now we would get this A would be equal to minus 1 by rho del P plus G. Now this acceleration, it is system acceleration. We already know from our unit 2 that this is equal to capital dV by capital dt. Okay. And we also know that how much is that equal to? That is equal to del V by del T plus V dot del V, and this would be equal to minus 1 by rho del P plus G. And this is our Euler's equation. Now beauty of this is that this is in coordinate free form, meaning by that you can have this equation, its shape would not change. Doesn't matter if you are analyzing in XYZ coordinate system, r theta z, r theta phi, it makes no difference. Now the only thing you need to know is what is del for each of these particular coordinate system. Once you know that, it's quite easy, and this thing you can very easily get from your first year mechanics book. So the equations we have are mass conservation and now this Euler equation for inviscid flow. Okay, we have these two equations up till now, but how many flow variables do we have in this equation? Let us look at that. The flow variables we have in the Euler's equation. We have velocity, velocity vector, density and pressure. These are the three we have. Now to support the Euler equation, we need to have two more equations. Okay, three variable, three equation. So one is Euler equation. Next is our let's say this is our equation A. Next is our continuity equation or mass conservation. We already know about it. It's 1 by rho by del T plus d rho by dt plus del dot V equals to 0. This is my equation B. And the third equation which I need would be the equation of a state. Equation of state. And that would be that my density is a function of temperature and pressure. Okay. Or for those cases where I'm considering the density is a function of temperature and pressure, this would be the case. Now I can solve any kind of flow, even compressible flow using this. This is for a journal case. But now I have introduced one more variable. So the number of unknowns here at this stage, the number of unknowns which I have are density, temperature, pressure, velocity. I started with 3, but because of equation of state I have added another one. So therefore, to match the number of unknowns with the number of equation, another equation for temperature is needed, so that I can get unique solution for given boundary and initial condition. Now the temperature equation can be obtained by applying first law of thermodynamics to a fluid particle. But in our case here, let's say we can also take a case where there is no energy is being exchanged. Okay, for an adiabatic case, we can consider that this density is only a function of pressure, and that can only be done when we are talking about a single temperature. We are not varying temperature. Okay, so if we can get that, then we would have only three unknowns, that is density, pressure and velocity, and we have three equations: mass conservation equation, which gives us a relation between density and velocity. We have Euler's equation, which gives us a relation between velocity and pressure, and then we would have a third equation, which would be equation of state, okay, which would give us a relation between density and pressure. Okay, so let's say we have pressure, we have velocity, we have density. So the relation between density and velocity can be obtained from mass conservation or continuity equation. The relation between pressure and velocity can be obtained for inviscid flow from Euler equation, and the relation between pressure and density can be obtained from equation of state. Again, this is the case where I am considering that density is dependent on pressure only. There are no energy exchanges happening. But let's say if I would go to compressible flow, or for even an incompressible flow, if there are energy exchanges happening, then I need to bring another variable, which would be temperature, and because of that I would need another equation which I would get from first law of thermodynamics, and I would have to apply that first law of thermodynamics to a fluid particle to get that equation. Now let us consider incompressible flow only now, and let's see what do we have with that. So for incompressible flow, we have del dot V equal to 0. Now this is coming from mass conservation equation, and from linear momentum equation we would have del V by del T plus V dot del V equals to minus 1 by rho naught. It's constant now, that's why 1 by rho naught del P plus G. Now this is what we have for an incompressible flow, these two equations. Okay, and you can see two equations and two unknowns. We have pressure and we have velocity. Density here is constant, it's not changing, and that's why we have incompressible flow. The density is not changing with pressure or temperature here. Now one of the uses of Euler equation is to obtain pressure distribution in a moving field if the velocity field is known. So let's say if you know the velocity field, and what do we mean by to know the velocity field? Many a time you would have heard this velocity field. Let us talk about it. What do we mean by velocity field? In the Viva I also asked this question, and many a times I thought that it is not clear. So let's say this is an aerofoil and we have a uniform velocity here, but as soon as we would try to focus our attention that how velocity is changing in 2 or 3 dimension. Here let's say if my coordinate system is x and y, and unit vector along x is, let's say, I, along y is, let's say, j. For uniform velocity in this way I can write it as ui. U is the magnitude and it is in the direction of I. But once I would come near to this aerofoil, then at different values of x and y, each point which I am showing here represents a coordinate point. x or y value. Now at each of these points there would be some velocity vector at each of these points. So basically, if I am writing my velocity vector and it is changing in any way, let's say axi plus byj, this thing is known as velocity field. Okay, this is known as velocity field. Many a time it is easy to find velocity field experimentally or through equation. So we are saying that Euler equation is Euler equation can be used to obtain pressure distribution in a moving fluid if velocity field is known. So let's say if this v vector is known, then using Euler's equation we can find the value of pressure, and it can go the other way also, that if we know pressure field, from that we can find velocity field. And it is quite easy. So let's say as a practice problem, take v equal to axi plus byj and try to find pressure. Okay, pressure field. Try to find pressure field, and you can do that. Try to do that, and let us see what you would get. Okay, provided that this g is equal to minus gk, it is along z axis, okay, and provided that let's say at the origin this pressure is equal to P naught. If that's the case, then you can modify the equation above and you would get something like this, that minus del P by rho naught del x, this is equal to a square x. Please look at the sign. Would it be plus a square x or minus a square x? You need to look at that. Minus 1 by rho naught del p by del y is equal to a square y. Just see if it is a square y or if it is minus a square y. Just look at that. This is something which you can work out and you can find out. And 1 minus rho naught del p by del z, okay, minus g equals to 0. Now this is something which you can work out, and this is how you can find pressure field once you have velocity field for an inviscid incompressible flow using Euler's equation. Okay, next we would move on in the next lecture. We would move on to concept of motion pressure in incompressible flow, and we would talk about Euler equation in streamline coordinates, and this is the work which we would do in our next class, and maybe we would move on towards Bernoulli's equation through Euler's equation.